Welcome to the Rory Academy YouTube channel, where we present information that helps you improve your understanding and knowledge about power electronics technology and its emerging applications. Today, we will focus on the power electronics technology associated with Tesla Model S. In the year 2021, 11,555 Tesla Model S cars were sold. Tesla's Model S is known for its longer range, faster acceleration, and dazzling speed, and the credit goes to the power electronics and the battery systems. The Tesla Model S can travel up to 1,610 kilometers, which is about 1,000 miles, on a single full charge. It is currently one of the most expensive Tesla brands in the market, and about 20,301 units have been sold this year. The Tesla Model S battery system consists of the following. The cooling system in Tesla Model S is based on propylene glycol, which acts as a coolant. To improve the heat transfer efficiency between each battery cell and the battery cooling system, the coolant tube running inside the battery pack has a wavy profile. Such a profile increases the contact surface between the battery cell and the coolant tube. Battery Management Systems (BMS) is the most important component in a battery pack, essential for the battery pack safety. The BMS used by Tesla in Model S is based around Texas Instruments BQ76PL536AQ13-6 series cell lithium-ion battery monitor and secondary protection. The red encircled area of the BMS shows that it contains 6 monitoring ICs for each series connection in the module. The yellow encircled area shows the terminals where the connection from the 6 cells will be connected. The IC by TI used in the BMS can be daisy-chained to need only one communication connection to the system. The BMS is integrated into every module and monitors the battery life, temperature, and charge-discharge cycle of cells. The Tesla Model S consists of a battery pack with 18,650 lithium-ion battery cells. The cells are cylindrical in shape and have a dimension of 18 mm in diameter with 65 mm in height. The nomenclature of the cell can be easily understood by splitting the numbers into 3 parts. The first 2 numbers tell us about the diameter of the cell in millimeters, the third and fourth numbers tell us about the height of the cell, while the last digit tells us about the shape of the cell. At a nominal voltage of 3.66 volts, each 18,650 cells can be charged as high as 4.2 volts, with each cell storing up to 3,400 mAh. Each 18650 cell can be discharged as low as 2.5 volts. The Tesla Model S uses multiple 18,650 cells to make the battery pack. But rather than arranging all the cells and making a single big battery, Tesla uses multiple smaller batteries called the battery module to make the final battery pack. Each battery module is based on the 6S74P configuration, in which 6 battery cells are connected in series, and each of these series has 74 cells connected in parallel. Each of Tesla's modules is rated for 500 amps of continuous current with 750 amps of peak current. There's a liquid cooling integrated to maintain the temperature of the battery pack. The pack has a configuration of 6S74P, and which makes the total number of cells to be 444 cells in each battery module. The cells are arranged with the positive or negative terminals facing up in a specific pattern, to achieve the desired voltage and capacity for the battery module. The red cells indicate cells whose positive terminals are facing up, and the white cells indicate cells whose negative terminals are facing up. In a Tesla Model S battery pack, 16 battery modules are assembled inside a battery tray. Each of these 16 modules is connected in parallel to the central bus bar in the battery pack through the M8-bolt terminals on the battery module. The battery pack central bus bar collects current from all the modules and takes it to a contactor, which feeds it to the electric drive. The 18,650 based battery pack of the Tesla Model S is rated at 400 volts, which is floor-mounted in the vehicle. The rear drive unit is located between the rear wheels. The front drive unit is located between the front wheels. The Tesla Model S uses a 3-phase 2-level inverter topology with an input battery voltage of 400 volts, arranged in a triangular structure. The conventional 3-phase 2-level inverter consists of a DC link voltage and 6 switching power semiconductor devices. As mentioned previously, the conventional 3-phase 2-level inverter consists of a DC link voltage and 6 switching power semiconductor devices. In this case, a conventional two-level inverter structure with 6 IGBTs paralleled per switching device to handle the high current. The inverter structure of the Tesla Model S is shown in 3 dimensions. On the topmost layer of the inverter structure, we have the control board, which coordinates the flow of voltage and current in the inverter topology. After the control board, we have an aluminum shield that separates the control board from the phase current sensor ferrite ring. Afterwards, we have the gate driver board, which consists of the gate driver IC circuitry for switching the IGBTs in the inverter topology. Then, the phase busbars that connect the IGBTs to the printed circuit board, PCB, which contains the gate driver board. Then, we have the heatsinks that enhance the heat dissipated from the IGBTs. The 36 IGBTs attach to the heatsinks and connected to the PCB through the busbars. The IGBTs are based on the 2247 package, which is a 3-lead through-hole device with a metal plate for a heatsink. Then we have the IGBT clips that connect the 2247 packaged IGBTs to the DC link capacitors. The IGBT, insulated gate bipolar transistor, takes the best parts of both BJT and MOSFET into a single transistor. It takes the input characteristics, high input impedance, of MOSFET and the output characteristics of BJT. With 3 terminals, namely, the gate terminal, collector terminal, and emitter terminal. Applying a gate voltage to the gate terminal, which is more positive than the emitter, whereby allowing the electrons from the emitter to flow from the N+ region into the N drift region of the IGBT, while the holes from the collector are injected from the P+ region into the N drift region. Due to the excess of both electrons and holes in the drift region, its conductivity increases and starts the conduction of current. Hence the IGBT switches on. In the next series of videos, the power electronics technology deployed in the other Tesla model brand will be addressed. First thing you need to do now is subscribe to the Rory Academy YouTube channel and enjoy our weekly videos on power electronics technology in emerging applications, such as electrified transportation.